This was an example where they were going to get ready to forklift out a ton of equipment on their network and throw a ton of money at it. And I'm like, guys, wait, before we do that, let's find root cause. Let's make sure that we're directing our funds in the right direction and at least isolate the box that it's coming from. So, and then this we were able to do with these examples.
Hey everyone, it's David Bombal back with Chris. A lot of you have given a lot of great feedback about the TCP IP Deep Dive video, and we're asking where's the second video? So here we go. Chris, welcome.
Hey, it's great to be back, David. Looking forward to digging back into some more TCP. Let's go deep.
So what are we going to look at this time? Is there something specific?
Yeah, so we were talking and looking at some of the comments, and I think a good place to chat would be around the maximum segment size. That is an option in the TCP header. One reason to focus on this is because it's just often misunderstood as far as how it relates to the MTU, right? So the network, I mean, I know I'm preaching to the choir here, but the network has an MTU, an Ethernet MTU, you could even have an IP MTU. What does that have to do with MSS, and how does TCP, how can we help TCP with overcoming fragmentation or hitting its head on an interface along the path?
Yeah, so off camera, we were discussing something, and you were saying that maximum transmission unit, or MTU, is often misunderstood. Did you want to talk about that a bit, or should we just jump straight into Wireshark?
Yeah, actually, I think there's a video that kind of illustrates what I'm talking about. So why don't I show that real quick? I brought it. I'm just going to bring it in. So this is a video that I like to use in my trainings to talk about this whole subject. All right, so when we're learning how this whole process works, it's important to first think about how we can't just take any size packet and kick it out on the wire. And this is a video that sometimes I use in my training classes. This is actually a bridge that's in the United States, and they call it the 11'8" bridge, because this bridge is exactly 11 feet, 8 inches tall. And here's the problem, is that trucks will try to go under it, and it's a can opener. Bam! It just takes them out. So this is actually a whole video that you can watch on YouTube if you'd like to. And this happens enough to where, wow, this is a whole thing, right? So what does this have to do with network traffic and our subject? Well, really, we can't take a packet that's too big and just send it anywhere that we want, right? That is regulated, right? So first, let's talk about MTU and what that means. And like I said, David, I know you have a lot of experience in this, so I'm actually interested in hearing how you can contribute to the conversation for sure. So
no, I'm the dumb guy, so it's all on you, Chris. Come on.
Stop. Yeah, whatever. Okay, Mr. CCIE. All right. So basically, so at Ethernet, at the Ethernet layer, we have, and let me just draw this out for you. All right, so if I take Ethernet, right, so I have my destination MAC, source MAC, ether type, those are the fields of an Ethernet frame, and then I have this payload, and that's just my data, right? Oops, sorry, so wiggly. And then down here, I have my FCS. Okay, so this is 4 bytes FCS, this is data, and then we have, okay, dest MAC, source MAC, and then ether type. Okay, so ether type, or this is actually length type. Okay, so another conversation. But anyway, so this is where a station's going to put its destination MAC address, or its source MAC is here, where it's going is destination. But this data field, this is where this is variable, right? It depends on the amount of payload that I'm sending. Keep in mind, Ethernet can work with a lot of different protocols. You know, it doesn't have to be IP. It could be IPv6. It used to be, there were some other competing protocols at layer 3 that were really, really common. Data, this is a variable field. So basically, in the Ethernet standard, it was decided, okay, why don't we take that data and limit it to 1,500 bytes? Now, this is actually something that made Ethernet take off in the early years when there was a lot of competing layer 2 technologies, is because Ethernet, it was efficient in that it could carry 1,500 bytes, and it could do so with just an 18-byte overhead, okay? So 4 bytes here. If we add all this up, so I've got 6 bytes of destination MAC, 6 bytes source, and then this ether type is 2 bytes. So that's a total of 18 bytes of overhead to carry 1,500 bytes. That's not so bad. So this is why a lot of times Ethernet, you'll see on networking interfaces and routers along the path, you're often going to see that 1,500. And that's a good thing, right? It's a good amount of data to be able to carry across the link. Now, keep in mind, this is transmission unit. How much can I send? Well, in the days of Ethernet where you had, okay, I got Ethernet and inside this data, I've got IP. Let's just keep this simple. In fact, let's just draw this again because I don't like that. All right, so I just cleared that out just to be able to take a look at the data field. Now, let's just imagine that this is just that payload, okay? Now, let's take a look at the first 20 bytes. Let's just imagine this is IP, okay? So now this is 1500, all right, from side to side. All right, that's 1500. And IP is going to add 20 bytes as long as there's no options. And then the next
we have to say IPv4, right?
Oh, good call. Thank you. IPv4. If it's V6, then you got 40 here. Okay, so let's just work with V4 for a moment, because let's go back in time when we didn't have so many different types of fields and header values that we need to consider. All right, IPv4, and also the TCP header without options is also 20 bytes. That means TCP as a maximum amount of data that it can carry for a payload and still fit within the MTU is going to be 1460. That's why a lot of times if you're looking at your TCP handshakes and you see a SYN and you go down to that MSS field, we've done this on previous videos, you're going to see 1460 a lot of times advertised as an initial MSS. Okay? What that's saying is, hey, David, I'm going to connect to you. I'm the client. You're the server. I can receive 1460. Okay, so you can send me that. That's another reason why MTU and MSS are a little difficult sometimes, because MTU is maximum transmission unit. MSS is, hey, David, don't send me a payload any larger. It's kind of like a maximum receive unit, if you will. But that's MSS. So this is advertised in the SYN. It's only advertised once. This is just a beautiful, blissful, perfect world where there's no other protocols.
No VPNs.
No VPNs, no GRE tunnels, nothing else, no PP over E or any other type, or like you just mentioned one, no other IPv6, no other anything else that needs header space. So this is where protocols start to go, okay, let's roll back our sleeves and now we're going to start fighting for that 1500 while still having a payload that makes sense. This is where TCP can become involved. And this is where we can take this MSS that gets advertised in the handshake, and we can actually bring this number down so that we don't bump our heads like the 11'8" bridge. We're not going to smack ourselves into an MTU that is lower than the actual full packet payload. How are we doing so far?
Yeah, I think we just need to emphasize MTU is per hop, isn't it? So if you go across like a 10 gig, 100 gig interface, the MTU could be a lot higher. But if you go across, like we said, some other kind of interface, the MTU could be lower. And that's also a problem. And I don't want to jump the gun, Chris. I'm hoping that's where you're going to explain MSS and why this is a nightmare.
I think that's a great call. In fact, why Packet Tracer? Why aren't you coming up? So, actually, why don't I talk about that now?
Chris Greer actually uses Packet Tracer. Wow.
Yeah, I use Packet Tracer.
Wow.
I mean, but okay, here's my beef with it though. Can't capture and export PCAPs out of it. So points for GNS3. All right, where are we? So let's go ahead and go into our MTU. So we were actually just talking, David. So this interface, this is just a basic network, okay? We got two routers, right? We got a router here, we got a router here. Now, this is where, and don't worry about my sniffer in the middle, okay? So this is where we could have an Ethernet interface on one side. We could have a 1500 over here, okay? And in the middle, we could have a different MTU. And that's where, like I said previously, if we just had a flat Ethernet network with no other considerations, just 1500, 1500, 1500, 1500, this conversation isn't as complex. The complexity comes when we start needing to have different MTUs along the path. I'm just going to say 1436. Or we have to start accommodating for other technologies such as IP tunnels and GRE and IPsec. And if I have, take another type, like a point-to-point protocol over Ethernet, that's going to borrow 8 bytes from the payload. Those technologies, depending on what I have in the middle, that's going to reduce the MTU along the path.
Yeah, I mean, it becomes a nightmare. Like I was just thinking, and we don't want to take it too extreme, but like VXLAN, IPsec, GRE, like you said, PPP over Ethernet. I mean, there's so many of these. And then you get the crazy stuff where it's IPsec over GRE and then over MPLS. How many times do you want to like do this? So you've got all these different technologies adding and stealing, if you like, from that MTU. So bit of a problem. So
yeah, absolutely.
I don't want to jump the gun again, Chris, because I remember, I'll just tell a war story while we're here. I remember...
Ooh, war stories from David Bombal, everyone. War stories. Let's go. Let's hear it.
I remember doing like VPNs years and years ago, and it was a nightmare because, GRE, IPsec VPNs across the internet for many, many sites around the world. And it's like, okay, you've probably experienced this as well, where a ping works. Ping's great. But people complain that the network is slow. So, my pings are great. Network's fine, but nothing goes through. And that's exactly this problem, isn't it? Because large packets are being dropped. Sorry, go on.
No, you're fine. I mean, I would never want to jump in on a war story from David Bombal. That's exactly right. But what you just said is exactly why a lot of times for me on my side, coming from the packet world, that's when I'll get called. Pings work. The path works, things are still slow, and why? And a lot of times that can happen even if somebody doesn't realize it, if they migrate to a new technology, if they even add one thing, but it breaks another. And that's why I'm super passionate about this topic, because you got to understand what's happening end to end. See, David and I, if you and I are communicating, especially over TCP, we have zero knowledge of the network underneath.
Yeah. I mean, you're in California, I'm in the UK. How many hops is there? There's a lot of hops, different technologies. We have no visibility of that. Yeah, I remember this. I remember reading a document on Cisco's website talking about MSS and MTU. Took me a while to understand it. So, Chris, hopefully you're going to make it simple for everyone watching. No pressure.
Yeah. No problem. Let's do it. I'm up for the challenge. So, first of all, let's just. How is it that I've gotten so far into a video with you so far, David? And I haven't had Wireshark open.
Yeah, I'm a bit worried about you, Chris.
Yeah. I'm falling off. I'm falling off my game. All right, everybody. So. It took me way too long to get to this PCAP. I'm sorry, but here we are. Okay, back to the fun. And let's go ahead and do this. You can kind of see what I've done with this profile. I'm in my TCP plane profile, and I'm just going to take a look at this first packet. This is a SYN, and I'm going to come down into the handshake and take a look like we did on previous videos. You guys already know this. This is old hat now. We come down to options. Maximum segment size is 1460 bytes. Okay. In a perfect world with maximum capability, this station can receive 1460. 1460 plus 20 byte TCP header plus 20 byte IP header, no options. That gives me 1500 in a beautiful, blissful, perfect world. Okay.
And the reason for that is just to make sure everyone understands, this PC has an Ethernet network card in it. And that's why we get to the 1460, yeah?
That's how, so 1460 will be the payload, but TCP is trying to stay under the 1500, which is the card. Yeah. The card's like, the TCP goes, oh, we're Ethernet, cool. All right,
I'll just say this, Chris, I don't know if you can bring up your Mac. Sorry to take you on a tangent. So if you look at your Mac Ethernet settings, like network preferences on your Mac, so on your Wi-Fi connection.
Oh, yeah, sure.
So if you go to network preferences,
and
you go advanced, hardware. So we can see the MTU 1500, yeah? So if you go manually.
Good call.
If you set that to manual, if you go to the MTU there, you could set that, like if you had a 10 gig card in your Mac, you're going to want to up that because the MTU on like 100 gig or 10 gig or 25 gig interfaces, you're going to want to make it a lot bigger than that to get the throughput. Otherwise, it's too slow.
Yeah. And that's if you have to have a full, you got to have a network that understands everything in the middle. Yeah, that's a good point. I like that.
So I mean, I need to post that video. I'll link it below once I've posted it, showing you how I connected a 10 gig interface to a Mac. And then the throughput is low through the switches until you up that. And I mean, there's lots of videos like that on YouTube. Yeah.
So cool. Honestly, that's new to me. I didn't know you could change that. Wow.
Yeah, you have to, because otherwise you'll never get your like 10 gig full line rate.
And does TCP change its MSS after that?
So, Chris, just remembering what you spoke about, like 1460 and 1500, because TCP recognizes the Ethernet MTU. If I increase the Ethernet MTU, then the MSS will adjust. So if I make the Ethernet MTU 10,000, then the TCP will be bigger based on the headers. Yeah.
Yes, and that actually gets us into jumbo frame environments where we have larger connections, or we have a system end-to-end that understands we can use larger MTUs.
Yeah.
So that's where we want to be careful. Just because I send out, if I had the capability, just because I can send out a 8,000 byte frame, what if the next switch next to me can't accept it, or the next router can't transmit it, right? So end to end, we have to have that understanding that jumbo frames work.
Yeah.
So that's just but typically in most environments, end to end, you're going to see 1500 as an MTU.
Yeah, I mean, Chris, just for the real world, I mean, you are troubleshooting client networks, not always in a data center. So, I mean, those large frames are typically in a data center, aren't they? Even though it might change now because, people are getting gig to their homes and even higher speeds these days. But, I mean, today in the real world, it's typically 1500, yeah?
Yeah, absolutely. And that's going to be a limiter for a time.
Yeah.
But one day they'll go, you know what, Ethernet was written in the 60s, so let's go ahead and move forward. We'll find out.
So, Chris, I just want to make sure that everyone gets this. What is the difference between MTU, maximum transmission unit, and MSS, maximum segment size? Can you just explain, very quickly what those two are and the differences between them so that everyone gets that piece?
For sure. It depends on basically the layer we're talking about. All right, so let's go Ethernet layer 2. How much data can it send out on the wire? What is its maximum transmission unit? So a lot of times you're thinking switches, you're thinking router interfaces. What is the maximum transmission unit for Ethernet? MTU.
Okay.
You can also have an IP MTU, but most of the time we're talking that Ethernet MTU. Maximum segment size. See, keep in mind that Ethernet deals in frames, IP deals in packets, TCP deals in segments.
That's great. Yeah.
So when I get a huge drop of data down from an application, it just goes thunk down from, here, TCP, deal with this, and it's 10K. TCP looks at that data. It's a stream-based protocol, so it goes, how much can I put in each segment? How much of this 10K can I chop up? It doesn't really care, but it's got to know, well, I don't want to make anybody upset down below with the Ethernet interface. So it's going to work in tandem to figure out, what do we got to work with? No? Okay, 15? Cool. All right. So that tells me the maximum segment size that I can put as a payload within the actual packet itself. Now, just to make sure everybody's clear on that, this is just I'm just going to draw out a whole frame. So this is the Ethernet component. Okay, so Ether. Keep in mind there's headers. So Ethernet, and let's just deal, just for simplicity, IPv4. We'll tackle IPv6 on another video. So I got Ethernet, IP, TCP, and then I have my actual payload. Now TCP does not care what this payload is. All right?
Yep.
It doesn't care. Any application. This is MSS. The maximum amount of data that I can carry within a payload. Does not at all include the TCP header, the IP header, or the Ethernet frame. So right here. So this is, let me go here to here. That is MSS. And that as a maximum, it can be 1460. That's because the minimum TCP is going to be 20, IP 20. The Ethernet frame is 18, but that's not even accounted for in the MTU. The MTU is from here to here. So Ethernet goes, my payload is 1500. That does not account for the Ethernet frame, any VLAN tags, any other layer 2 stuff that might be appended after the payload. So the Ethernet payload is the MTU. The TCP payload is the MSS. And that's why these two concepts can be a little confusing sometimes. Okay, so since we're talking about 1 gig or less interface, that's what I'm dealing with here. So I'm talking about standard Ethernet. I got to fit it underneath 1500 bytes. That's my budget. So TCP is going, in a perfect world, IP is 20, TCP header is 20. That gives me 1460 for a max payload. And again, this is an advertisement of, hey, David, you can send me 1460. Okay, so let's take a look at the opposite direction. I'm not going to look at any of the other options for now. Let's really focus on MSS. I even added this as a column here. So 1460, the server in the opposite direction says, cool, yeah, I can also do 1460. Now keep in mind, this is not a negotiated number. The server could say 1432, 1400, 1300. And that just means I will send 1460 to you, but you cannot send 1460 to me. You got to send 1300 of what or whatever I advertise. Not negotiated. This is an advertisement of the MSS. This is never repeated again. This is in the handshake. So this is, again, why it's so important to capture a handshake. So let's take a walk down this PCAP. This was a PCAP that was given to me by a friend named Vladimir. He's got a really cool blog. Maybe we can link that down below about this exact problem. And the reason why I like this example is because of what I'm about to show you. And that's where two endpoints can actually do something called path MTU discovery. Let's learn how that works. Okay, so we're basically transferring a file. I'm not going to worry too much about NetBIOS session service and the application up above. Okay, we're just moving a simple file. And it's not until, let's keep our eye on this segment size. If we come down here, we're going to notice, all right, ignore that for now. Just trust me. Okay, boom. Big packet, big packet, big packet, big packet. So right here, the server is trying to send across, I know it's the server because the source port's 445. He's trying to send a 1460 over to the client. 1460, big packet, big packet, big packet, then less than big packet. So this is just a block of data. Right away, we get this destination unreachable fragmentation needed. Whoa, okay, wait a second, hang on. Let's go back up to this first packet, this first big one. And if I come down into the IP header, if I take a look there, it says don't fragment is set. What that means is, hey, router, or any router or any device along the path, do not fragment. Don't break this up into different segments. IP can fragment. That means David, if you send me a huge frame, I can break it up into smaller ones, add a new IP header to each one, and then send it along its way. It goes all the way to the receiver. The receiver then pieces it all back together and then ingests all that data. I have an IP fragmentation video on my channel if anybody wants to get a bit more into how that works. Okay, so DF was set. This means don't break it up, okay? And in fact, in a TCP thread, most of the time, all packets have the DF bit set, okay? Because TCP is like, I don't like fragmentation. I don't want to fragment. Fragmentation does a few things. First of all, I got to bother a router with splitting things up and adding a new header. It's not as efficient. And now my endpoint, David, you now have to bother with reassembling everything. So if I'm dealing with a fragmentation situation, my throughput goes down because now we have to add another process like fragmentation. So TCP wants to be efficient. Don't fragment me. But we hit this router here. This is 1.1. Let's just check this out. Let's inspect this. Okay, so IP header. And let's take a look at the ICMP message. Destination reachable, fragmentation needed. Uh-oh, we hit our heads just like that bridge, right? We hit an 11-foot, 8-inch bridge. But this is what's interesting. In this packet, this is where the router can advertise the MTU of the next hop. So this is called path MTU discovery, where the router is saying, hey, 1300 is what I have next. And you just sent me a 1460 without the actual big headers. You actually sent me a 1500 byte packet. I got to break this thing up. I got to take this payload, snap it up, and I got to add some new headers, send this along its way. So this packet goes back to the sender. Let's take a look at the next packet. So now the sender goes, oh, I ran into, remember, let's remember that, 1350. Next packet. Okay, so the TCP segment length here is 1310. So now we take 1310, we can add a 20 byte TCP header and a 20 byte IP header. Now we're at 1350. So the sender got the hint. He reduces it, he sends it, that one gets through, or we don't see that retransmitted down here. And if I take a look at the next packet, now this has a TCP segment length of 150. Well, if I add those two things together, I'm back up to my 1460 bytes. So now I just took those 1460 bytes, split it off, 1310 in one and 150 in the other. And then that data can move along. And I noticed that the sender did the same thing with those other large packets. So that is path MTU discovery.
Yeah, I've got to remember it's been a while since I've done that. Years ago that I had that huge issue with the VPNs. But Cisco devices allow you on a tunnel interface, as an example, to type IP path MTU discovery or something. I'll put the actual command below. Because if you don't do that, the routers just drop it, don't they? And they say, sorry, tough luck. And I don't know if this is what you found on your like troubleshooting war stories, Chris, where if someone doesn't do that on a tunnel, so let's say they put it across a VPN tunnel or something, that's where the pings work, but all the traffic, well, you can't send traffic through because like if you, the typical issue I've seen, pings work, but you can't open up a website, or a website is really slow or something like that. Wherever you're sending larger packets, it's slow, but the pings are fine. And that's because the routers are not communicating back to the clients that path MTU discovery is available, and the routers are not communicating that back. Is that some stuff that you've seen? Yeah.
Oh yeah. What you just said is exactly it. The route. First of all, the router has to be capable of doing this.
Yeah.
Advertising the next MTU. Second, that it needs to be enabled, so it needs to generate the thing in the first place, and then that ICMP message needs to make it back to the endpoint. So if a firewall or some other device in the middle could drop it, and then the endpoint needs to react to it.
Yeah, so our endpoints are currently, Chris, you're doing this every day. Windows, is that the default is MTU path discovery is on now, is that right?
It should, yeah. And the reason why I say should is because I haven't seen it actively in the wild in a little bit. It's been a while since I've seen a PCAP like this. So that's why I borrowed this one with Vladimir, because I think it teaches the point very well. But as far as in the wild, I just haven't seen, do TCP stacks on these different operating systems still react to path MTU discovery? Okay. So yes, in theory. Have I actually seen it at the packet level? It's been a while since I've seen it at the packet level. But back to what you were saying, one thing that can trip people up, especially when talking about MTU versus MSS, let's go back to the ping example. All right, so you mentioned, okay, pings work, but anything else doesn't. Okay, so why is that? Well, okay, let's just do this. Let's just ping David Bombal.
It's a bad website.
All right. Well, look at it from my perspective, right? David Bombal, he's a whopping. Actually, I'm going to stop this. All right. What can we learn here? So first of all, if I bring this in, all right. So yeah, boy, latency, but that's not your fault. Also TTL. Okay, we learned in previous videos that gives me a guess as far as the number of routers I'm going through. Looks like I'm going through 10 routers. Right. I'm guessing you started at 64. And here's my 64 bytes, right? So 64 bytes was put into an ICMP packet. Basically, it's a very small amount of data. That's a lot of times why a ping will work in this scenario. We're not really stressing things. So something that I'll do, and we'll just come in and we'll start to tinker with that length field. Okay, so let me just clear. And you can do this on Windows or Mac or Linux, any of them. Let me just do a ping, but this time I'm going to change. This is basically the packet size. And let's do this. Let's make this thing 1500. And I'm going to ping David Bombal. Okay, and you know me, I can't not capture this while we're doing it. So just because it's fun to learn side by side. And this is what I encourage everybody to do. I mean, do these tests on your pings and these types of things that we show you, but capture it at the same time, because that's when you can really understand the flows and what's really happening. So I'm going to come in here and I'm going to go ahead and do capture. I see some traffic coming in. And what I'm going to do is I'm just going to say ping-s 1500. So that sets the packet size, or wait, does it, to 1500. This is what's tricky. Well, I get a lot of people saying, oh, goodness, oh, okay, let's just see if stuff works. Now, this does work, but let's actually see what happened. Let me come in here. I'm going to stop. I'm going to do ICMP. And if I come over here, I can see my total length is 1500 bytes. Wonderful. Okay, expanding IP. And if I come in here, let me see where my total length is 1500. So wonderful. So, but 1508. So let me actually just remove. I'm just going to remove this. And I'm going to take your address, David, and I'm going to drop this up as the destination and actually flip the direction. Just call it adder. Okay. So now I got both directions of traffic. But check this out. I got one packet that's 1500. The total length is 1500. But I had 8 bytes of ICMP, right? So this still was a big packet. In fact, the other data that I sent, so this is actually 1500. Now keep in mind, that's the maximum packet size. Take out 20 bytes for the IP header, and then I need 8 bytes for ICMP. So in that first packet, I'm only able to send 1472. And then in the next packet, I'm able to send the rest of the data, the other 28 bytes. And that gets me up to, this is why I said, this is not an advertisement of the actual overall packet size. This is the amount of payload that I want to send to David Bombal. So my system fragmented it because it had to, because of the NIC limitation of Ethernet. That's what I'm going over from this system. Let's do this. I'm going to add, what I can do, so I can do -D. Now, if you're in a Windows system, you use -L to set the length, and you use I think it's F, like lowercase f, to do not fragment. So what I'm doing is I'm telling ping, send a ping, but don't break it up. And what does my system do? It goes, whoa, wait a second. Right. So you're trying to send 1500 bytes, Chris. Like, let's back up. 1500 bytes with an ICMP header, which is 8, and then you want to send another 20. So, buddy, you're 28 bytes over budget here. We can't even send that out the front door.
Yeah, I mean, your local computer's doing that because the network card is, as we looked at through this preferences, is 1500, and you're trying to squeeze too much in. So immediately it's kicking it back to you. Yeah.
Correct. Yeah. Correct. And I don't even see a single packet out here because my system's going, nope.
Yeah.
Now, let's try this. See, this is where I'll talk to my clients and they'll go, oh, we have an MTU problem because we can't send 1500s. Remember, when you're pinging with a 1500, that does not take into account the IP header itself, right? That's why up here, 1508, that does take into account. It's advertising. It's saying, hey, I added 8 bytes for the ICMP header, but this gets put into an IP packet that then needed to be fragmented. As soon as we added the do not fragment bit set, that's where we got in trouble. Okay, so let's do this.
So if you set it just below, I don't know if, sorry, I'm jumping the gun again, Chris, like 14,
you're okay.
Whatever it was, then it should go through, yeah?
Let's try it. Let's try 1472, do not fragment bit set, and I'm going to come over here. Let me just start my capture again. I'll leave that filter just in case your IP doesn't change on your site, depending on where it's at. There we go. Okay, so we're seeing some traffic go through, and let me go ahead and stop the ping. We're going to come back here. Let's go ahead and take a look at our first packet. So this is don't fragment. The total length is 1500, but if I come down here, the data itself, so 1464. So if I add my 8 bytes, that's going to bring me to 1472, which I said I wanted to send. So I basically threw 1480 out there on the wire minus the IP header. If I go 1 byte more, 1473, then message too long. Sorry, buddy, you're over budget. You're 1 byte over budget. Okay, so you want to see a cool trick with a Mac system? All right, so if you're not sure, I kind of ran into this one the other day, you can just do a range of MTUs on a Mac system. Honestly, I haven't tried it on a Windows system, so I don't know if you have, David. But all right, so basically I'm saying start at this range and then stop at this range. So that's the low G, big G, and you can look at the help menus and it's all in there for you. Let's do 1480 just for grins. I'm going to say do not fragment. Oh, actually, I need to say what's my interval. How much do you want to go up for every attempt? And then I can do -D, and now I can do that's do not fragment. DavidBombal.com. Boom. So check us out. 1476, 77, 78, 79, 80. All right, we hit our ceiling.
That's nice.
Right? So that tells me now, but let's remember something here. This does not take into account our IP header. So we're still good at 1500. On the wire, our MTU is still 1500. The reason why I wanted to show this to everybody is because I've worked with a lot of customers where they'll come in and they will basically ratchet down their MTUs locally because they think that the network in the middle can't carry 1500 because their pings stop at 1480. And I go, whoa, hang on. 1480 doesn't include the IP header, so you're still good at 1500. No reason to drop it. Now, this is where we're going to get into the topic of TCP MSS clamping.
So the client thinks they need to set it to 1480, is that what you said?
Yeah, so the reason that this is relevant is sometimes I'll work with clients and I'll see them actually changing on systems local TCP MSS values.
On their client PCs. So they go to like
Correct.
1,000 PCs and they try and change it, yeah?
Thank you. Or they do it on the router.
Okay, yeah.
They'll tell the router to. So, and I'm going to get into an example in just a minute. That's getting into our war story. So the router can actually reach up when it sees a TCP SYN and it can change an MSS. So that way I don't have to go to all these other systems and change the MSS. If I have a GRE tunnel, if I'm doing any kind of point-to-point over E or anything that's going to borrow header space upstream, and I need to reduce the payload, instead of going to every system and saying, hey, TCP MSS, let's reduce this, I can do it on a router level. That way, every SYN that passes by, I just reach up and change the MSS. I'm sure that's a value you've seen in the wild too, or have set yourself. But as far as what to set it to, sometimes I'll be working with clients that have set 1480 or 1472 on their routers and say, well, we have to change this, we have to clamp TCP because we have an MTU problem. And I say, well, what gave you, why'd you think that? And they go, well, look at my pings. It stops at 1480. That means I have a path along the way. Well, I have a router along the way somewhere that I'm hitting my head under, right? I'm hitting my head with 1500s. So I'm bringing it down to 1480. This is where this is misunderstood though, because when you send a large ping, and this is the takeaway point. If you're swimming in detail a little bit, don't worry, capture some pings and check it out in Wireshark. But just take this away. The ping output will only show you the payload. You always have to mentally add 20 bytes to these numbers you're sending.
So in other words, it should be 1460. Header. That's what you're saying, yeah?
Yeah. So for example, getting back into Wireshark, let me flip back now. Let's flip back over to that PCAP again. So now if we get back into our PCAP, we understand a little better why it's very common to see TCP SYNs with a maximum segment size of 1460. We need some space. TCP and IP. Now that's in a perfect world. What about when TCP has some options in a packet? So for example, timestamping, or if there's a packet that's lost and I need to do selective acknowledgement. Those are topics we're absolutely going to be hitting in the TCP Deep Dive series. Don't worry, everybody. But those are things where TCP header might increase in size. It could be I have a TCP header of 32 bytes because I have some options that I have to make space for. That will affect my payload. The system accommodates for that. TCP is going to go, oh, I have a larger TCP header. I can't put 1460 in this thing. Let's go ahead and reduce that guy down to 1420 or whatever it is. That way I have some more room for this header and I'm still staying under my bridge of 1500 bytes for the Ethernet MTU.
Yeah, so that's on the local device. And are you going to talk about MSS, like configuring that on a router or something to advertise that back to the client, or is that a separate conversation?
That's getting into my war story.
Okay, great. I keep going to the war story.
All right, I've kept you hanging long enough. All right, so let's do this. Okay, so let me set it up here, guys. Okay, so let's go ahead and talk about the problem that was experienced. So first of all, let me just set up the complaint. It was exactly what you just said, David. Pings work fine, and we try to open up a file, and it takes forever, right? Or we try to pull a file down from a shared drive. We try to open up and retrieve emails. Anything we do, initially, we just see this like spinny wheel for a time. And then after that, it's laggy, but it eventually works. And those are the tricky ones. Not broken. If things are flat out broken and there's a broken path, that's easier to resolve than it's slow, right? And especially, hey, pings work. So the path is okay, so to speak, but moving data isn't. All right, so let me just build this scenario for you. This was the client side of a capture that we took, and I went ahead and I scrubbed off. There's no data encapsulated. I changed the port numbers and changed the IPs. So literally, the Basically, the timing is all that's preserved and some of these other values. Okay, I'm actually going to hide this for right now. Let's go ahead and come up to that SYN. Okay, so the SYN, if I come down here, I'm going to take a look at my options. I got maximum segment size 1460, window scale 8. So I have a large TCP window, receive buffer that I can work with, and we're using SAC. Awesome. Okay, like muscle memory, as we're working through Wireshark, I want everybody to start to do this. It should start to become automatic. I'm sitting client side because here's my latency is between my SYN and SYNAC. SYNAC comes back 86 milliseconds later. That's my network round trip time. Okay, so I was able to hit my endpoint, port 80, and he comes back. Let's check out that SYN. All right, maximum segment size is 1432. Okay, that just means I have to send 1432, but he can send 1460. Window scale is 0. This is just a trick on server side, especially if a server is sending data and not receiving it. It's just a way of activating this option without it actually needing to multiply to a huge window. This is something you'll see on servers. Kind of another topic, but basically it just means, yes, you can use window scaling, David. That's awesome. SAC permitted, and then yes, we can do selective acknowledgement. Cool, so there's our handshake. Let's come down. Client sends 350 bytes to server. The next thing that happens, just around my network round trip time, I see 93 milliseconds later, I see data come in, but previous segment is not captured. What that means is I had a jump in sequence number. All right, so we learned about this on the last video. We were talking about sequence numbers and how they increment. Basically, look at our jump. So this sequence number started at 1461, and we're sending 563 bytes. So the next sequence number will be 2024, but this one is 1461. I send this to you, David. You act back 2024 so that I know you got my 563. That's what the server's trying to do here. But wait a second, time. 1461, where was the 1460? This is the first packet we see come in from the server. So we go, as a client, we go, cool, AC1, because I didn't get that 1460. If I come down into my SAC field, 1461 to 2024, what that means is I got your 563 bytes, but I'm missing 1460. You got to fill in the sequence numbers between 1 and 1461. Where was that big packet? Right away, that was an indicator to me that we were running into an MTU problem.
Yeah, so someone along the path dropped it.
Correct. Somebody along the path dropped it. Well, this is where things get fun. 21 full seconds later. This is sequence number 1. 21 full seconds. We sat around spinny wheel, and then all of a sudden, boom, and then things start going. Well, looking at the packet level, hold up, 536. This is from the server. I'm capturing client side. We wait 21 full seconds to start to get this data. What on earth happened in 21 seconds? It's a long time. I don't like waiting. Okay, so let's go ahead. Well, you don't like it. Wait, you don't like waiting either. We are impatient folks these days. So let me come into, this is where I said, okay, and this is getting into the point, everybody, of multi-point captures. From a client perspective, I was able to get some clues off the wire that we were looking at an MTU problem, something maybe even with MSS clamping. This continued to work, but now I realized, hang on a second, we only have part of the picture from the client side. Keep in mind the server side, it's experiencing something else. It's doing something in 21 seconds. Let's go find out what. And this is where we come into the dual side capture. All right, so what I'm going to do, I'm just going to move this guy over. I'm on a Mac system, which makes it a pain to start up two applications at the same time. So I'm just going to do open-n/applications/wireshark.app, which I should turn into a little, I'm lazy, that's why I haven't done that. Anyway, let's go ahead and drop in my server side PCAP. Let's do this. Now, okay. Let me just resize. Clients on left, servers on right. This is as real world as it gets. If people show me that 21 seconds, I say, I got to get a client side trace. I got to see what's going on the other side. For right now, time doesn't really matter. I'm going to just pull this in. Actually, you know what? Let's take a full look at this before we go too far. Now, the first thing I thought was just fun and weird is that big red line there. That's helpful. So SYN IP total length is 64. Well, the complaint, if I expand this out, IP says total length exceeds packet length, which is 52 bytes. The actual, that's 52 minus the Ethernet frame itself. So the true frame size was 70 that was on the wire itself. Because we can see up here 66 bytes on the wire. Wireshark doesn't account for the FCS. That's the 4 bytes on the very end. It just says, okay, there was 66 bytes. That's including the Ethernet frame. But hey, IP, you're saying that you have 64 all on your own. So as soon as I add 18, this is broken. Here's what's weird. If I take a look at the original SYN, look at the IP header. Total length is 52. When it was received on the server, the total length was 64. Client lets it go at 52. Server receives it at 64. And this is the same IP ID, 4081, 4081. Someone's changing something in the middle. We get that sense? Yeah, like what's that about? Okay, so there's a clue. Let's just keep going. It still worked. Okay, so our SYN still got there and the SYN ACK was returned. So that's why another tip for the listeners or the viewers, if you see some weird looking thing, some flag and things keep going and it was quick, that's probably not where you're troubleshooting, right? Like it's a clue that you store away, but don't get too hung up on every little flag that you see in Wireshark. Otherwise, you're never going to get past these black lines and red letters. Sometimes they're involved, sometimes they're not. The thing that I look for is the complaint was slow. So I got to go find where slow is. And down here, if I look at my delta time, whoa, that's full seconds. This is what they called me for. Okay. So SYN, SYNAC. And if I come down to let's take a look at our options. So we have our MSS came in. All right. So MSS came in. MSS came in 1460 bytes and I return it and check this out. 1460 bytes. Hang on. Server lets go of 1460, but I receive it and 1432. Noted. Filed away. Okay. So let's keep going. So SYN, SYNAC, ACK. This is that 350 that comes in from the client. Then right away, the server sends a 1460 almost immediately. This 1460 starts at sequence number 1. This 1460 never makes it over to the other side. It hammers 2 packets out there. 1460, 563. The 563 made it. That's the 563 over here. The 1460 didn't. I can see that side by side. And ACK comes in from the client. The server goes, it waits. Basically, this is a full retransmission timeout. This was 3 seconds. Now, TCP has evolved since a little bit where it's not going to wait quite as long. But at this stage of the game, we're still building it's called a congestion window, and also our retransmission timers. The server's still trying to figure out, well, I don't want to retransmit too quick because what if this packet's still in flight somewhere in the world? So it waits 3 seconds and then it sends a 1460. It retransmits. Well, now it goes into its doubling mechanism where, hey, after 3 seconds I tried, let's go ahead and try again, but I'm going to double the time. 6 seconds. Still nothing. This is called basically an MSS black hole or an MTU black hole. We didn't get any ICMP data back from the network. That nice ICMP message that was fragmentation needed wasn't coming back. The path MTU discovery wasn't coming back. It was either disabled on a router somewhere or a firewall was blocking it. Probably disabled on a router somewhere. So the server had no recourse. It's like, okay, 1460, 1460. Now this TCP stack did something interesting. This is where the server goes, you know what? Let me just try 536. Now 536 is an interesting number that it tried. This is basically the minimum. I'm going to try to say this well, David. This is the minimum maximum that you can receive as an IP station. If you're an IP station, I expect, because of, if you go look it up in the standard, you should be able to receive a packet of 576.
Okay.
At least. And that's in the IP standard.
536, yeah.
576.
Okay. 576, all right.
If I take off the IP header, 556. If I take off the TCP header,
I'm glad
536.
I'm glad you said that, yeah.
So this is TCP going, this is basically the last ditch effort of trying to get data across to you when you're not accepting a large packet. The station was like, here's the minimum max packet that David can receive. Let's just try it. So he sends a 536 and it worked. Whoa, he got that packet. Okay, let me try this one. Let me try this one. He got those. Whoa, okay, here's the rest of my data. And now for the rest of this, see, 1432s are coming across from you. But now for the rest of this entire throughput, for the rest of this connection, I'm scared to try anything bigger than 536.
So it basically slowed the whole thing down, is that right?
Yes, it slowed the entire throughput after we overcame this retransmission time. So now going back to client, this 21 seconds was burned because we were waiting on 3 retransmissions from the server with a big packet. Finally, the server was like, 536. Whoa, that worked. Okay, you have a David, you have a very, very low, it's either an MTU or you as an end station. But we're hitting our heads here, so let me just drop my, I'm tall, so this happens sometimes. I go through a door. It's like, let me duck under that. Problem is, though, is that once that happened, the station never tried anything larger. Now, this is where TCP implementations and flavors can vary. On another station, maybe it would have tried again at a larger value. I'm going to be honest, what I would have expected after a few retransmissions, some stations would even send a reset and say, you know what, I'm sending these retransmissions across. I try 3 times. If you're not there, I'm out. I'm going to go ahead and drop the connection. So that's where it just depends on implementation, the type of server that it was, the stack that it was using, and those little, I call them nerd knobs that are inside that TCP stack.
I mean, it's a nightmare, Chris. So, okay, so you saw the client, you got the capture from the client, you saw that there was a problem, you kind of thought it was MTU, that was like sort of the hint, and then you had to get a capture from the server. But what happens if you couldn't get the capture from the server?
Well, see, now experience would tell me I got to go look for an MTU problem. And the reason is because data that is coming across jumped 1460. That's experience, right? So that tells me, and also if I take a look at that MTU coming in, I would go, maybe the server knows something I don't know, 1432, right? So maybe here was, everybody ready for the punchline? Want to know what it was?
Yeah, I was going to ask you because I was hoping, okay, so what was the solution? Because that's what everyone wants to know. Yep.
I know. Well, I'm going to go to Packet Tracer and I'm going to show you. All right, just to illustrate this. Okay, if I bring this back in. So let's basically, so the WAN in the middle, I had no knowledge of, and I still to this day, let's just draw a cloud, a puffy cloud. Yay. All right, big black hole. I don't know what was in there, but this is what we found. Okay, so this was a client talking to some server over here. Okay, so keep in mind, I let go of a SYN and it had 1460 in the MSS. That arrived over here at 1460. Then in the return path, he let go of 1460 and it arrived at 1432. All right, so this is where what we did is we found that there was a router here that was doing MSS clamping. What that means is there's a command in there, and David, again, I'm preaching to the choir here. Basically, when you see a SYN, take out the 1460 and replace it with 1432. The reason, I don't want to do this on every single end station. I'd rather just have the router do it because I got stuff I got to make room for in the middle. GRE tunnel, any number of things that are happening. Basically, hey, payload, get a little smaller because we need some headroom here for a WAN technology or a tunnel in the middle. Here's the problem. This router was upgraded. This was upgraded at the local office, but that command wasn't restored, the MTU or the MSS clamping. So what that meant is this happened in the outbound direction. See, the server or the router, when it received a SYN, it would change the MSS. So it receives it at 1460 and it would let it go at 1432. And it would just go across and arrive at the endpoint. But the 1460 in the opposite direction would be maintained by this router here. So what we had to do is go in and we had to fix that. We had to say, okay, let's just clamp that down to 1432. Every time you see a SYN, let's clamp it, 1432. That'll give us some room up above. Now, 1432 is kind of an interesting number to me. And that's where and basically that's the punchline. That's what happened. As soon as this was restored, things got working. And let me tell you why. Things started working because now, oh, look at that. Let me get rid of that. Okay. Things started working because now the ingress MSS, if I took a look at that SYN coming in, now the server knew don't send anything larger than 1432. Don't send that. The problem was that the clients were telling the server, hey, I'm good with 1460. You can go ahead and fill all of these packets to the brim. Problem is that we were hitting our head on that bridge and the server was trying to compensate for it. But once this SYN came across and gave us 1432 to work with, then the server could go, oh, okay. And it reduced the payload. And then now we were able to make it under whatever in the middle needed that extra head space, which I never found out exactly what it was, but I knew that it was something that took some extra headroom like a tunnel.
Was it a Cisco device or was it another type of device, those routers?
It was a Cisco.
Can you remember the command they were typing?
Yeah, you know what? I'm glad you asked. MSS Adjustment. So this is from the Cisco site. The actual configuration. See, everybody, okay, audience, real quick. Can you imagine preparing for an interview with David Bombal?
Can you zoom in there, but Chris, sorry.
Yeah, so what we did is we found that this is MTU clamping, right? So the router's getting involved here. It sees a SYN and it adjusts the MSS down. And again, why? Because that prevents you from needing to do it at every endpoint. For me, I was like, okay, this is great, but let's learn more about what's in the middle and let's even maximize it. Like, what if 1432 is, let me tell you why. Let me tell you why that number caught my attention. Okay, so let me go back to my little drawing here.
Yeah, sorry, Chris. Right. I didn't want to put you on the spot. It's just there's another command that I'm thinking about called IP MSS.
If you this was one that
I'm going to link a document below because I've actually got a Cisco document where they've got that exact command. IP TCP adjust MSS, but there's another one that I'm pretty sure that exists that
there's more than that one.
Yeah.
Let me see. Is it in this document?
See, you're better prepared than I am.
See, I knew you were going to ask that question. This is a big world to get into because once you start like really looking at MSSs and how to tweak them and tune them. All right, well,
that's the command I'm looking for. Tunnel path MTU discovery. Because what you can do, you can advertise and just for everyone watching, I mean, I'll confirm it in the description perhaps because this is like old memory for I think Chris and I.
Yeah, but it's important to know how it works.
You've got to, because what you're supposed to do if you like create a GRE tunnel or something is you've got to advertise the MSS. Sorry, you've got to advertise the MTU to the clients. And then the clients, Chris, I think it's true today that most clients will support MSS. So you advertise the MSS to the clients and then they automatically adjust the MSS based on that setting. So you don't just hard code it. You advertise that this is the maximum segment size for this link. And the clients that'll allow them to work out the maximum segment size along the path. But I like what you've done because you've shown like a real world problem where something went wrong.
Yeah, it did. And even to the case you were just talking about, it's back to what are the myths that people believe and what are some things that get adjusted maybe without understanding it fully. For example, in this case, they were like, well, we were told to disable ICMP replies. Had you not done that, then PathMTU would have told the server what the actual MSS was, or we would have been able to get in and find out what the true one was. Because basically in the middle, we were dealing with a tunnel that was taking up space where that previous command would have been helpful, right? That I showed you on how to ramp up your packet size until you hit your head. But basically, this is what I did with 1432. I was like, I think this is what happened. As far as how we ended up on that number, because if you take 1432, this is what my brain did with that. If I have 1432, okay, as a MSS clamping on the router, what that means is that if that's my max, then I've got my TCP 20 bytes here. All right, that's TCP. And that brings me to 1452. And if I come up here with my IP, and that's assuming we're not running IPv6. If we're running IPv6, then just take an extra 20 bytes off of all of these numbers. Okay, so IP 20 bytes. So now we're sitting at a packet size of 1472. And I was thinking, how do we end up on 1472 as a full packet size? And they're like, well, that's the maximum ping size that we could get through. And I said, oh, that's where we're at. Because if we say 1472, that's not, again, then my max packet size. We got to think about this also is going to add this is going to add the ICMP header and the IP header on top of this payload. So I didn't actually get to work with them much further on this. I mean, here's the problem sometimes that I run into, David, is sometimes when things get working, then it's like, okay, go away.
Yeah.
And I go, wait, no, let's do more testing. And they say, yeah, but it works. Go away. So anyway, this number often tells me it's like, okay, we got a ping of 1472 through, so we're clamping. We're clamping our TCP MSS based on that successful ping, but the ping isn't taking into account the ICMP and IP header addition, the 28 bytes that could also go through. So that's where I was like, I mean, I don't even know if we need to clamp this network, because if you're getting 1472 through successfully as a ping, that means you're really getting 1500s. Your total packet length, once you add, again, ICMP. So on the let me draw this better. Sorry. If you're getting 1472 byte pings through, well, 8 bytes of that is your ICMP header, or you can add ICMP 8 bytes to it. And then also there's a 20 byte IP header. You are at 1500. If the biggest ping that you can get through is 1472. So this number was interesting to me because I think they were assuming 1472 was their MTU. So now you have to drop it down 40 bytes to get to the TCP MSS of 1432, right? So I don't know. Maybe there was something in the middle that was we did have to take into account for, but this change, again, root cause, let me back up here. Root cause was... over here on the receiver, I was getting 1432 from the server. The server was advertising 1460, but in the opposite direction, that clamping didn't happen. The server thought 1460 was still legit. That was getting dropped by a router. So yes, we did have an MTU clamp in the middle somewhere, but the receiver never knew. It never knew that it had to reduce its MSS because the outbound router usually took care of that. So anyway, that's my
Show us the
war
Cisco
story.
command again. Sorry.
The Cisco command.
Sorry, the problem having me on the call is I'm going to want to see Cisco again. What was that? That Cisco? You had that PDF, I think.
This one.
No,
okay,
that's another
MSS.
document. Was that
this is another one. It's the same command.
Is that the one you had? Yeah.
It's the same command. Yeah.
Okay, so the problem was someone typed that on a Cisco router on one side, and then they disabled ICMP. Is that right? Replies or something? What did you say?
Correct.
Yeah.
So this was enabled on the outbound router from the server, and then routers in the middle were not responding to ICMP, or they were not the ICMP messaging was disabled, and then that would have told us which router along the way had the lower MTU, and then we could have made a decision from there, right?
So, and then the solution was to do this on both sides.
We needed to do this on both sides. Yeah.
I think what I'll have to do, Chris, is I'll put some links below. I've only got there's a bunch of Cisco documents, like we've grabbed some. But what's nice is like often on the Cisco documents you read the theory about it, but you don't see a practical example like this of like a war story nightmare. And so it's great to. That's what I love about like you and I. I'm not sure if I'm allowed to say this, Chris, but you and I have often discussed, like Cisco people like me may know like the Cisco commands and stuff, but when it comes to this, sometimes they get lost or they misunderstand. And you come from the Wireshark point of view. So it's great to see this, man. So thanks so much for sharing.
Sure. And, just as easily, you start working through Packet Tracer and looking at commands and looking at buffers and looking at things that I'm lost. So, packets aren't the imperial truth of everything, and that's just the only truth there is. I mean, there's a lot of other important data sets out there, but for problems like these, especially the weird ones, that's usually where I think, okay, Wireshark, let's actually see what's happening on the packet level to then be able to make a decision going forward. This was an example where they were going to get ready to forklift out a ton of equipment on their network and throw a ton of money at it. And I'm like, guys, wait, before we do that, let's find root cause. Let's make sure that we're directing our funds in the right direction and at least isolate the box that it's coming from. So, and then this we were able to do with these examples.
My takeaway from every time we talk and every time I talk to someone is you never stop learning, do you? It doesn't matter how long you've been doing this because things change. And I remember how many years ago? I'm talking like 15 years ago or something. I was dealing with this on VPNs and stuff 20 years ago. I don't know, a long time ago. It's still the same problems in a lot of networks, but stacks change and commands change and stuff like that. But we still often deal with the same old nonsense. Yeah, I like to say, you keep forgetting things, but it comes back again. So, Chris, again, this video is getting a bit long. I want to thank you so much for sharing. I don't want to kill it. Is there anything else you wanted to say before we wrap it up?
Yes, actually, if you don't mind, I know we're limited on time, but that just reminds me, there was one last little thing, a feature I wanted to make sure everybody knew. With Wireshark, so this is just a quick little PCAP. Maybe I can share this one. But if you come down to, there's a few TCP threads here, but a feature called, if you right click and do follow TCP stream, that'll pull the stream data out, and then you get a thumbs up. So that means you can like. Okay, so hey, look, everybody. This isn't the packet's telling you to like. Okay, it's not me.
Like the video, I like it.
It's right there. And then I think there's another feature in this one too. I didn't show you this yet. If you just go to, I think this file. So if you ever have HTTP, you can go to export objects, HTTP. And there's a really cool thing. If you ever have JPEGs, be careful. This is where malware, we're going to have a malware conversation again. But if you have a JPEG, you can also preview it, which is kind of fun. And then, there's a subscribe button. So there was a like and a subscribe in the PCAP. I mean, come on.
That's brilliant. Well done. So you got to like and subscribe to the video. Is that kind of what you like hinting at?
I mean, the PCAPs are saying that. I mean, that's it. No, actually, this is a fun one to generate. I'll share it with everybody if they'd like.
That's brilliant, Chris. Again,
right,
thanks so much, man.
Great to chat with you, David. Have a good one.
I'll just say this to everyone who's watching. Chris and I are like, it feels like we're opening up a can of worms here. It's just like more and more stuff. But let us know, do you want us to go even deeper into this stuff? I'll put a bunch of links to Cisco's website, which I found useful, and stuff that Chris has found as well. But if you want us to go even more into the crazy depths of this stuff, let us know in the comments below. Thanks, Chris.
Bye, everybody.